Welcome to your Final Control Mechanisms Physiology Laboratory. Today we'll be conducting the thermoregulatory activity. We will begin the laboratory with Activity 1, Thermal Physiology. Approximately 75 to 80% of the energy converted into ATP from carbohydrates, fats, and proteins is lost as heat during energy conversion processes in the human body. These losses do not mean the energy is destroyed, but energy is converted. You will recall that the science of measuring heat production is called calorimetry. In this laboratory, we will use the method of partitional calorimetry to compute body heat storage during exercise in the heat. This method is a form of indirect calorimetry. The principle of partitional calorimetry is based on deriving the amount of heat stored in the body from separate analysis of different avenues by which the body gains or loses heat. Now, heat is thermal energy transported from one site to another due to a temperature difference between the two sites, the body and its surroundings. This heat transfer ends with the temperatures of the two sites being equal, causing a thermal equilibrium. By summing the heat transfer through these avenues, we are able to indirectly arrive at the amount of the heat the body will store. From our perspective, we shall consider our closed system to be a fire suit in which our subjects will be cycling. Within this system, the total amount of energy will be conserved, but the energy will change forms. Chemical potential energy from carbohydrates, fats, and proteins will be converted into mechanical energy. This is the external work performed on the cycle ergometer. And finally, the heat energy within the body. The mechanical energy passes to the ergometer from the subject, where it is converted into several other forms, such as heat energy from friction, kinetic energy via the movement of the ergometer and the surrounding air. The human body handles heat energy released during ATP synthesis in two ways. It can store this heat, or it can pass this heat to the surrounding environment. If this heat energy is stored, the body's temperature will rise at the rate of 1 degree for every 3.47 kilojoules of heat stored per kilogram of body mass. An average 70 kilogram person will change mean body temperature by 1 degree for each 243 kilojoule change in heat energy content. During exercise at 200 watts, in a thermoneutral environment, our hypothetical person would consume approximately 2.5 liters of oxygen per minute and experience a total metabolic energy use of 1,000 joules per second. About 800 joules per second of this energy would be converted to heat energy. This would cause the total body temperature to rise by 1 degree in just over 5 minutes. If we assume a pre-exercise body temperature of 36 degrees and a maximal upper limit of 41 degrees, then our person would reach this point in 25.5 minutes. Yet, people frequently exercise for several hours at this work rate without becoming hyperthermic. Clearly, heat energy is being dissipated to the environment. The aim of this laboratory is to introduce students to human temperature regulation measurement. We will compare the body's response to exercise in a heated fire suit versus a non-heated, non-fire suit environment. We will also quantify the avenues of heat transfer using partitional calorimetry. This later purpose will be achieved by calculating the components of the heat balance equation using data collected from exercising subjects. This equation is derived from the first law of thermodynamics. Before we dive into the practical, it's important to understand a few equations, as well as the two most relevant laws of thermodynamics, to better appreciate the results we see today. The first law of thermodynamics states energy cannot be created nor destroyed but remains constant in a closed system. This is demonstrated well in nature. Bushfires, for example, exhibits an example where the energy expelled in the form of heat and light is representative of the energy required to make the trunk, branches, and leaves of the tree. In relation to our experiment, the energy in the form of glycogen stores, chemical bonds of glucose and ATP must be equal to the heat produced by our exercising participants that remains in the body, the mechanical force that was exhibited during the activity, and the energy that is dispersed into the environment as heat. The second law of thermodynamics is about the quality of energy. It states that as energy is transferred or transformed, more and more of it is wasted. The second law also states there is a natural tendency of any isolated system to degenerate into a more disordered state. This is explained simply with the following calculations. The whole body heat balance equation given below, indicates the M, which is the energy produced by metabolism, equals the work or the energy used to perform the activity, plus the stored energy as heat, the R, or the radiative heat exchange, C, the convective heat energy exchange, E, the evaporative heat energy exchange, and K, the conductive heat energy exchange. We can rearrange the equation to determine heat storage. This can be listed as a positive for storage or a negative for loss. The equation S equals M minus W E R C N K. Page 2 of the laboratory manual indicates the variables that I've just listed, with S equaling heat storage, M, the internal heat production or metabolism, W is the energy used to perform the work, E is heat exchange via evaporation, which can be thought of as a heat loss as water vapor from our skin as sweat. R is the heat exchange via radiation, which occurs between the skin and solid bodies of the environment. A good way to think about this is when you hug your partner and you feel the heat coming off their skin. C is heat exchange via convection. Convection is the heat transfer by a fluid, either air or water, carrying the heat between body and environment. Think wind hitting your body. K equals heat exchange via conduction. Conduction occurs when body touches solid material of a different temperature. This is demonstrated by a dog laying down on a cold pavement to try and cool its body. As it's difficult to evaluate the energy that we store internally, we can extrapolate the energy by deducting the energy we lost to work performed in evaporation, radiation, convection, conduction, and metabolism, as these are all measurable variables. This calculation is given. A final note before we begin. Since our core body temperature remains in a very fine range, around 36.5 to 37 degrees, at times we give off more energy than we keep. This is seen when going from a cold climate to a hot one, where the body will begin sweating and evaporative heat loss measures would increase. Similarly, if you went from a hot to a cold environment, evaporative heat loss measures would decrease. For this reason, heat exchange can be lost from the body, so R, C, E, and K values can be negative or positive. To assess the thermoregulation mechanisms of the body, we've recruited 2 participants to conduct an identical 20-minute cycling activity, with one wearing gym clothes and the other a fire suit. The purpose of the fire suit is to assess the changes in the way the body attempts to remove heat as the participant approaches steady-state hypothermia. Measurements taken in this activity include cardiac frequency, FC, core body temperature, skin temperatures at 3 distinct sites, total body temperature, baseline and post-exercise body mass, as well as blood pressure. Before commencing the exercise, subjects were required to bring their own exercise gear and towel, with the fire suit participant bringing long pants and a long sleeve shirt. A consent form should be obtained with all risks and benefits explained to the subjects. To begin with, baseline body weight and height should be recorded and entered into Table 1A, found on page 4 of your lab manual. The subject should be seated and at rest in a grey supported back chair, while the team members compute the subject's baseline body surface area using the calculation provided on page 3. Baseline blood pressure measurements should be obtained and added to Table 1A. While this takes place, 3 skin thermistors should be applied to the subject's mid-ventral thigh, mid-dorsal forearm, and mid-pectoral chest. The 3 skin sites will be used to determine the mean skin temperature, given as TSK average on Table 1A. Results should be obtained as part of the baseline measurements. The 4th skin thermistor should be cleaned with an alcohol swab and gently placed at the entrance of the left auditory canal and fixed in place with some tape. This will be used to measure core body temperature, and baseline measurements should be obtained before beginning the actual cycling. Once both the fire suit and non-fire suit participant are ready, they should begin cycling at a work rate of 100 watts or 60 revolutions per minute, as indicated on the ergometer, for 20 minutes. As the participant cycles, the data team will begin taking results and applying them to the relevant fire suit or non-fire suit tables found on page 4. At the conclusion of the 20 minutes, all relevant data points should be recorded and the participants should disconnect all thermistors, towel dry, and be weighed to assess the weight loss as a result of sweating. Now that the participants have finished cycling, and all data has been collected, the following results should be copied into your lab book for both Table 1A and 1B, each representing the non-fire suit and fire suit participant respectively. Question 9 on page 8 of the lab book can be answered by comparing the differences in variables between the fire suit and the non-fire suit at each stage of the 20-minute cycle. To begin answering this for yourself, begin by asking, was there any difference between the two conditions? If so, try and explain why using the physiological mechanisms of thermoregulation and relevant learnt physiology. Likely differences may be a change in heat storage, evaporation, mean body and skin temperatures between the individuals. Don't forget that the practical is designed to create two distinct conditions that either benefits the thermoregulation or creates a barrier to its efficacy. I'll go through each thermoregulatory mechanism in more detail to provide a broad understanding that may assist in answering this question. A vitally important and high-yield concept for control mechanism physiology is the idea of the thermal steady state. With the onset of exercise, heat production as a result of contracting muscle fibers and the breakdown of molecular bonds to fuel movement increases. A proportional relationship is exhibited between heat production and exercise intensity, which we see every single day. Someone who prefers to run will generate a lot more heat and sweat than someone that decides to walk. When you exercise long enough, heat storage in the body increases, which results in an increase in core body temperature. Thermoreceptors in the body detect a change and begin to respond via the integrated preoptic anterior hypothalamus, POAH. The afferent nerve signals will be transduced, and effort output will result in greater heat dissipation to prevent hypothermia. The body's response occurs by shunting blood to the periphery to increase apical blood flow to the skin to promote sweating. This will result in the excessive heat produced in exercise being dissipated to the environment, preventing the core body temperature to increase to potentially life-threatening levels. This is known as the temperature plateau, where the generation of heat equals the loss of heat. While initially, the core body temperature increases before it plateaus as the body reaches steady state hypothermia. The average skin temperature reduces as a result of the effective cooling done by evaporative heat loss. The top graph shows that with an increase in metabolic heat production, the body's thermoregulatory mechanisms kick in with convective, evaporative, and radiative heat loss measures attempting to return the body's core temperature back down to a normal level. One of the major methods of heat transfer is completed by radiation. This is the radiant energy that flows down a gradient from warmer to cooler areas and can be rationalized by imagining being in a cold room with lots of people in it. The room would quickly heat up with the radiative heat loss of all the people contributing to the increase in room temperature. Radiative heat loss accounts for approximately 60% of heat lost when at rest, but has a very minor role during exercise. The second method of heat transfer is convection, which occurs in proportion to the difference between the skin and ambient temperature. Cooler air will absorb heat much faster than warm, humid air. So, if an ambient temperature is colder than the skin, then convective heat loss will occur more rapidly. This is demonstrated by traveling to a humid environment and trying to cool down from a breeze. Conversely, if you would exercise and begin sweating, being outside in a colder, windier environment, convective heat loss would provide a greater means of heat loss than, say, radiative or conductive heat loss mechanisms. The third mechanism of heat transfer is conductive heat loss. This is a minor mechanism of dissipating heat from the body into the environment and requires the transfer of energy directly into an object cooler than our skin. The rate of transfer of conduction is dependent on the temperature difference between the two objects. Generally, heat loss or gain is minimal, particularly during exercise where the surface area in contact with the cooler object might be only your shoes when running, for an example. Radiative, convective, and conductive heat loss methods are found to provide minimal effects and were hence combined as a single variable in this practical. As you can imagine, as both participants continue exercising and their core temperatures reach steady state hypothermia, their apical skin temperatures would also increase proportionally. This occurs as a result of heat in the blood being shunted to the periphery as a mechanism to cool the core. Conductive heat loss would only occur between the participant and the ergometer, where they are touching on the hands, feet, and bottom, and hence would provide negligible heat transfer. As radiative heat loss requires a temperature concentration gradient for it to be effective, the fire suit, as well as the subject riding with exercise gear on, would experience an instant increase in the temperature around their immediate area, and a concentration gradient would therefore be diminished. Finally, convection as a means of heat transfer would not occur indoors, where no air or water currents can remove the ambient air around the skin of each participant. One predominant thermoregulatory mechanism, however, is found to be effective in reducing core body temperature, and that is evaporative heat loss. As the main source of heat dissipation during exercise, evaporation occurs where a vapor pressure gradient exists. This mechanism is independent of skin temperature and environmental temperature, as it is effective in extreme heats. If you were to find yourself in a hot, dry location with low ambient humidity, a high gradient of water pressure between your skin and the air would create a fast evaporative environment. The only hindrance to this is hot, humid locations where the ambient water vapor pressure may equal or exceed that of the skin, in which case the body would struggle to compensate with these extreme conditions. In our practical, both participants utilize evaporative heat loss measures, as the other three mechanisms fail to prevent the body core temperature to stabilize. As the water vapor pressure of the external environment is drastically lower than the immediate areas around a participant's bodies, we find that both subjects utilize this mechanism predominantly, as you should see in your results. When comparing the two participants, the fire suit creates an added barrier for heat and humidity to escape. This would likely cause an increase in the water vapor pressure within the suit and cause an overall decrease in the effectiveness of evaporative heat loss. To compensate, the fire suit participants' core body temperature would likely increase, resulting in more blood shunted to the periphery to increase evaporation. This would result in the fire suit participant never reaching a steady state hypothermia level, and hence would result in elevated levels of sweat production, which can be translated into a larger overall weight loss at the conclusion of the activity. Many methods of heat loss rely heavily on the body's ability to shunt blood away from the core to peripheral vessels. Our bodies have tight control and regulation of its ability to direct blood flow in different environmental conditions. The non-apical skin has two types of sympathetic neurons that innervate vessels. In cold climates, norepinephrine is released from sympathetic fibers, which result in vasoconstriction, causing blood to remain in the core. You may notice your fingers and toes are particularly cold during winter, as your body tries to maintain adequate core temperatures to sustain life. During a thermoneutral state, passive dilution occurs where norepinephrine is not released and basal blood flow returns. During a thermoneutral state, passive dilation occurs when norepinephrine is not released and basal blood flow returns. Finally, during warmer climates, active vasodilation occurs through the release of acetylcholine from sympathetic fibers as well. This promotes heat dissipation when core temperatures are increasing by promoting more blood to return to the heart by superficial veins. Our skin receives approximately 10% of cardiac output, but can receive up to 50 to 70% in severe heat. Active vasodilation occurs indirectly through acetylcholine release, which directly innervates secretory parts of sweat glands. This results in the sweat glands' release of vasodilators known as bradykinin. To finish off, as we exercise, our bodies begin redistributing blood from our abdominal organs by the action of vasoconstriction to major circulations such as the renal, gastrointestinal, and urogenital systems. Our muscles are unaffected as a result of a metabolic metabolite, nitric oxide, which provides added vasodilation for the recruitment of more blood. This concludes your thermoregulatory classroom. Good luck with the remainder of the session.